Hello there, and welcome to Midnight Science, where curiosity slows down, the lights grow soft, and science takes the long quiet road towards sleep. Tonight, we are going to open one of the most famous boxes in all of physics. Not quickly, not dramatically, and not with the usual cloud of mystery that often gathers around the subject. We are going to open it slowly, carefully, scientifically. Inside that box, in the popular imagination, there is a cat, Schrödinger's cat. Perhaps the most famous animal in quantum mechanics, a cat that people often describe as both alive and dead at the same time. A cat used in lectures, documentaries, jokes, internet posts, philosophy debates, and sometimes, unfortunately, in places where quantum physics is asked to do far more than it ever promised. You may have heard the idea before. A cat is placed in a sealed box. Inside the box is a quantum event. If one thing happens, the cat dies. If it does not happen, the cat lives. Before the box is opened, people say, the cat is both alive and dead. It is a strange image, memorable, uncomfortable, almost impossible to forget. But tonight, we are not going to treat Schrödinger's cat as a slogan. We are not going to use it as a metaphor for positive thinking, manifestation, or the idea that consciousness magically creates reality. We are going to keep it where Schrödinger placed it, inside physics. Because the real cat was never just a cat. It was a challenge, a thought experiment, a way of asking whether the rules of quantum mechanics, when stretched from tiny particles to ordinary objects, lead to something deeply strange. The cat was designed to make us uncomfortable, not because physics enjoys being theatrical, but because the measurement problem is genuinely difficult. What counts as a measurement? When does a quantum possibility become a definite outcome? Does the wave function describe reality itself, or only our knowledge of reality? Can a system be in a superposition of different states? And if so, why do we never see ordinary objects, like cats, chairs, cups, or people, in obvious superpositions? These are not shallow questions. They are not decorations around quantum mechanics. They sit near its foundations. Schrödinger's cat is famous because it places those questions inside a simple image, a sealed box. A radioactive atom, a detector, a mechanism, and a living creature that should never have become a casual symbol for mystical confusion. Before we begin, I would love to know where you are listening from tonight. Is it late where you are? Are you listening in a quiet room, with the lights low, maybe letting this strange little corner of physics drift in the background? And if these calm journeys through real science help you relax, study, or fall asleep, consider subscribing. It helps this small corner of careful curiosity find others who enjoy learning softly in the dark. Now, get comfortable, let your shoulders settle, let your breathing become easy. There is no need to solve quantum mechanics tonight. Physicists are still arguing about parts of it, and they have had more than a century to make the argument very polished. You can simply listen, let the ideas arrive, one at a time. Let the words become soft markers along the path. Superposition, measurement, wave function, decoherence. Tonight, we will follow Schrödinger's cat back to the science behind it. We will begin with the historical problem that led to the thought experiment. We will see why Schrödinger proposed the cat in the first place. We will look at superposition without turning it into magic. We will examine the radioactive atom, the detector, and the mechanism inside the box. We will ask what the wave function is supposed to describe. We will look at the measurement problem, the place where quantum theory becomes most philosophically sharp. Then we will move toward the modern idea of decoherence, the process by which interaction with the environment makes quantum superpositions become effectively hidden from the classical world we observe. And near the end, we will carefully compare several interpretations of quantum mechanics, Copenhagen, many worlds, objective collapse, and other attempts to understand what the mathematics is telling us, not as entertainment fog, not as certainty where there is no certainty, but as physics. Slowly told. The story begins in the early 20th century, when physicists discovered that the microscopic world does not behave like the world of tables and planets. Electrons did not act like tiny billiard balls. Light behaved as both wave and particle depending on how it was measured. Atoms emitted and absorbed energy in discrete amounts. Radioactive decay occurred unpredictably, not because we lacked a better clock inside the atom, but because the theory seemed to give only probabilities. Quantum mechanics was not built because physicists wanted the universe to be strange. It was built because experiments forced them there. The old classical picture could not explain blackbody radiation. It could not explain the photoelectric effect. It could not explain atomic spectra. It could not explain the stability of atoms. The microscopic world kept refusing to fit the old frame. So a new frame was built, quantum theory, and it worked astonishingly well. It predicted experiments with extraordinary accuracy. It explained chemistry, solids, lasers, semiconductors, nuclear processes, Modern electronics. Much of the technological world around us quietly depends on quantum mechanics, but the theory came with a price. It told us that before measurement, certain physical properties may not have definite values in the way classical intuition expects. Instead, the state of a system is described by a wave function. The wave function can contain a superposition of possibilities, not simply because we are confused, not simply because we have not looked hard enough, but because quantum theory itself represents the system as a combination of possible outcomes. This is where the trouble begins. For an electron, we may accept that. For an atom, perhaps. For a photon passing through an experiment, yes. But what about a detector? What about a machine connected to the detector? What about a cat connected to the machine? If the microscopic system can be in a superposition, and if the detector becomes linked to that system, does the detector also enter a superposition? And if the detector affects a cat, does the cat become part of the superposition too? This is the uncomfortable bridge between the quantum and classical worlds. Schrödinger's cat lives on that bridge, or perhaps more precisely, it waits there, inside the box, asking us where the bridge ends. The thought experiment was introduced by Erwin Schrödinger in 1935. Schrödinger was one of the founders of quantum mechanics. His wave equation is one of the central equations of the theory. He was not an outsider mocking physics from a distance. He helped build the very structure he was questioning, that matters. The cat paradox was not invented by someone who misunderstood quantum mechanics. It was invented by someone who understood it deeply enough to see a problem. Schrödinger wanted to show how strange it would be if quantum superposition were applied directly to a large everyday system. A tiny quantum event would become connected to a large, visible consequence. An atom decays or does not decay. A detector responds or does not respond. A mechanism is triggered or not triggered. The cat lives or dies. If quantum theory describes the whole sealed system as a superposition, then the final state seems to include both outcomes, a live cat and a dead cat, combined in the mathematics. Schrödinger did not present this as a cute mystery. He presented it as a problem, a way of saying, look carefully at what the theory appears to imply. Look at how absurd it becomes when we scale it up without explanation. The paradox asks us to locate the boundary. Where does quantum possibility become classical fact? Is there a physical collapse of the wave function? Is collapse only an update of knowledge? Does the universe split into branches? Does the environment destroy observable interference between alternatives? Is measurement a special process? Or is measurement just ordinary physical interaction seen from inside a large, entangled system? These questions are still discussed today. Some parts are understood better than in Schrödinger's time. Decoherence especially has given physicists a powerful way to explain why macroscopic superpositions become effectively unobservable. But the full interpretation of quantum mechanics remains open. Different interpretations can agree on predictions while disagreeing about what is really happening. This is why we must be careful. Quantum mechanics is not vague. Its mathematics is precise. Its predictions are precise. Its experiments are precise. The vagueness enters when we ask what the mathematics means. What is the wave function? What is measurement? What is reality doing before an outcome is observed? Those questions are difficult, but difficulty is not permission to invent anything we like. A mystery in physics is still inside physics. It is constrained by equations, experiments, and evidence. That will be our rule tonight. No quantum mysticism, no magical observer, no easy slogans, just the real puzzle. A cat in a box is simple to imagine, but behind it lies a century of physics, particles and waves, probability and measurement, entanglement and decoherence, experiments with photons, atoms, detectors, and interference. A question about why the world we see looks definite, even though the theory underneath allows superpositions. So tonight, we will not ask whether cats are mystical. We will ask what quantum theory says, what it does not say, and why Schrödinger chose such an unsettling image to make his point, because the cat was never really the subject. The subject was the boundary between two worlds, the quantum world, where possibilities can combine, and the classical world, where a box is opened and only one outcome is found. And to understand why Schrödinger placed the cat there, we need to begin with the debate that surrounded quantum mechanics in the 1930s. A debate about reality, measurement, and whether the theory was complete. That is where the real story begins. Schrödinger's cat was not invented as a cute explanation of quantum mechanics. It was invented as a warning, a challenge, a way of saying, if we take this interpretation too literally, something strange happens. To understand the cat, we need to go back to the early 20th century, a time when quantum mechanics was becoming one of the most successful theories in science, and also one of the most difficult to understand. The old classical picture of nature had been powerful. Particles had positions, objects followed paths. Forces caused motion. If you knew the state of a system precisely enough, you could, in principle, predict its future. This was the world of Newtonian mechanics, clear, deterministic, comfortingly mechanical, but the microscopic world refused to behave that way. Light sometimes behaved like a wave, sometimes like particles. Electrons produced interference patterns. Atoms emitted light only at certain discrete energies. Radioactive decay happened unpredictably. The more physicists studied atoms, light, and matter, the more the old picture cracked. Quantum mechanics emerged because experiments demanded it, not because anyone wanted reality to become strange. The theory worked. That was the astonishing part. It predicted spectra. It explained chemical bonds. It explained the behavior of electrons in atoms. It gave a way to calculate probabilities for measurement outcomes with extraordinary precision. But the success came with conceptual trouble. The theory described systems using a wave function. The wave function evolved according to Schrödinger's equation, and that evolution was smooth, continuous, and deterministic. But when a measurement was made, the theory seemed to give a definite outcome. One result, not all possibilities. A detector clicks or does not click. A particle is found here, not there. An atom decays or does not decay. This created a deep tension. Before measurement, the wave function can contain a superposition of possible outcomes. After measurement, we observe one outcome. So what exactly happens during measurement? Does the wave function physically collapse? Does it merely update our knowledge? Is measurement a special process different from ordinary physical interaction? Or is the apparent collapse only something that appears from our limited point of view? These questions were already present in the foundations of quantum mechanics, and they still have not completely disappeared. In the 1920s and 1930s, Niels Bohr and Werner Heisenberg became associated with what is now broadly called the Copenhagen interpretation. This is not one perfectly fixed doctrine. It is more like a family of ideas. But in general, it emphasized the role of measurement, the limits of classical descriptions, and the idea that quantum theory gives probabilities for experimental outcomes. Bohr insisted that experimental results must be described in classical terms. We do not observe a wave function directly. We observe marks on screens, clicks in detectors, readings on instruments, outcomes in laboratories. For Bohr, quantum mechanics was not simply a picture of tiny objects moving along hidden classical paths. It was a framework for predicting and organizing what can be said about experimental arrangements and results. Einstein was deeply uncomfortable with this. He accepted that quantum mechanics worked, but he doubted that it was complete. He did not like the idea that nature at its deepest level was fundamentally probabilistic in the way quantum theory seemed to suggest. His famous phrase, often paraphrased as "God does not play dice," captures part of this discomfort. Einstein wanted a deeper description, something beneath the probabilities, something that would restore a more complete account of physical reality. Schrödinger too was uneasy. This is important. Schrödinger created the wave equation that bears his name. He was not hostile to quantum mechanics as a failed theory. He was one of its builders, but he was concerned about how the theory was being interpreted, especially when superposition was treated as if it could be extended without limit from microscopic systems to large ordinary objects. The cat thought experiment appeared in 1935. That same year, Einstein, Podolsky, and Rosen published their famous EPR paper, arguing that quantum mechanics might be incomplete. The EPR argument focused on entangled systems and the idea that quantum theory seemed to allow strange correlations between distant particles. Schrödinger responded to this discussion and introduced the term entanglement. He also introduced the cat paradox. So the cat belongs to a serious scientific debate, a debate about completeness, reality, measurement, and the meaning of the quantum state. It was not a meme before memes. It was a carefully chosen absurdity. Schrödinger wanted to show that if a microscopic superposition could become amplified into a macroscopic situation, then quantum theory seemed to describe a cat as both alive and dead. That conclusion was meant to be disturbing, not charming, not mystical, disturbing, because ordinary experience does not contain cats that are visibly alive and dead at the same time. We do not open boxes and find superposed animals. We find one outcome, alive or dead, not both. The thought experiment begins with a quantum event, usually radioactive decay. A radioactive atom has some probability of decaying within a certain time interval. Quantum theory does not predict exactly when a particular atom will decay. It predicts probabilities. If the atom decays, a detector registers the event. The detector triggers a mechanism. The mechanism releases poison. The cat dies. If the atom does not decay, the detector does not trigger. The poison is not released. The cat lives. The whole system is sealed inside a box. From outside, before looking, quantum theory seems to assign a combined state to the atom, detector, mechanism, and cat. A superposition of decay and no decay. Detector triggered and not triggered. Cat dead and cat alive. This is where the famous phrase comes from. But the phrase alone misses the point. Schrödinger was not saying, "Isn't it fun that cats are magical quantum creatures?" He was asking whether the standard interpretation of the theory had become absurd when applied to large systems. He was pushing the logic until it squeaked. The cat is a magnifying glass. It magnifies the measurement problem. A tiny quantum uncertainty becomes connected to a large visible outcome. Then we are forced to ask where the quantum description stops. Does the atom collapse when the detector interacts with it? Does the detector collapse when the mechanism amplifies the signal? Does the cat collapse a state by being alive or dead? Does the human observer collapse it by opening the box? Or is collapse not a physical process at all? These are different possibilities, and they lead to different interpretations. The original point was not that the cat literally proves one answer. The point was that quantum theory, as interpreted at the time, had a serious conceptual gap, a gap between the smooth evolution of the wave function and the definite outcomes we observe. This is the measurement problem. It is one of the central issues in the foundations of quantum mechanics. It can be stated simply. Quantum systems evolve according to the wave function. The wave function can be in a superposition. Measurements give definite outcomes. How, exactly, do definite outcomes arise? That is the puzzle. If we say the wave function collapses during measurement, we need to explain what counts as measurement. Is a detector enough? Is an irreversible record enough? Is the interaction with the environment enough? Is consciousness required? Most physicists today do not think human consciousness is the magic ingredient. That idea appears often in popular culture, but it is not required by standard quantum mechanics, and it is not the main scientific explanation for why we see definite outcomes. A laboratory detector can register an event without a person watching it in real time. The detector leaves a record. The environment becomes entangled with the system. Decoherence rapidly suppresses observable interference between macroscopic alternatives. The physics does not wait politely for a human mind. That does not mean the interpretation problem is solved in a single sentence, but it does mean we should be careful. Observation, in quantum mechanics, does not simply mean a conscious person looking. It usually means a physical interaction that correlates a system with a measuring apparatus or environment in a way that produces a record. This distinction matters enormously. Otherwise, Schrödinger's cat becomes a doorway to bad metaphysics. A way to say that the universe exists only when we look at it. A way to smuggle wishful thinking into physics. That is not what the thought experiment requires. The real issue is not human attention. The real issue is physical measurement. How does a quantum system become correlated with a measuring device? How are alternatives amplified? Why do we see one result? What role does the environment play? What does the wave function represent? These are serious questions, and they deserve serious answers. Schrödinger's cat also highlights a scale problem. Quantum effects are easy to observe in carefully isolated microscopic systems. Electrons, photons, atoms, small molecules, but cats are warm, wet, complex, macroscopic systems interacting constantly with their environment. Air molecules, thermal radiation, internal biological processes, vibrations, chemical reactions. A real cat is not an isolated quantum object floating in perfect silence. It is a living storm of interactions. This is why macroscopic superpositions are so difficult to maintain, not because quantum mechanics stops being true, but because the system becomes entangled with an enormous environment almost instantly. The alternatives lose the ability to interfere in any observable way. This is where decoherence will become important later. Decoherence does not necessarily solve every interpretation problem, but it explains why the classical world appears stable and definite. It helps explain why we do not see cats in visible superpositions. It shows how quantum possibilities become effectively separated by interaction with the environment. Schrödinger did not have the modern theory of decoherence in 1935, but his cat pointed directly toward the need for something like it. A way to understand how the quantum world gives rise to the classical world. The debate around Schrödinger's cat is therefore not about whether quantum mechanics works. Quantum mechanics works extraordinarily well. The debate is about what the theory means. That is why intelligent physicists can agree on the equations and disagree on interpretation. Copenhagen, many worlds, pilot wave theory, objective collapse models, relational interpretations, quantum Bayesian views. Each attempts to answer the measurement problem in a different way. Some add collapse, some remove collapse, some add hidden variables. Some change what the wave function means. Some place the observer differently. Some emphasize information. Some emphasize physical branching. The cat sits quietly in the middle of these debates, refusing to become simple. It asks every interpretation the same question. What happens in the box? Not as a story for children, as a test of conceptual clarity. If your interpretation can explain the cat, the detector, the atom, the box, and the outcome, then it has something to say. If it cannot, the cat remains waiting. This is why Schrödinger's cat has lasted so long. It is vivid, but it is not shallow. It compresses a deep problem into one image, a sealed system, a quantum event, a macroscopic consequence, a question about reality, and a demand that we not confuse mathematical probability with ordinary ignorance too quickly. When we do not know whether a hidden coin landed heads or tails, the coin is not in a physical superposition of heads and tails. It has one result. We simply do not know it yet. Quantum superposition is different. It is not merely ignorance, in the classical sense. At least, not in the standard formalism. A quantum system can behave as though multiple alternatives are genuinely combined, because those alternatives can interfere. Interference is the clue that superposition is physical, and not just a lack of knowledge. This is where we need to go next. Before we can understand the cat, we must understand superposition, not as a mystical blur, not as a poetic maybe, but as a precise feature of quantum states. A particle can be described by a wave function that combines different possible outcomes, and under the right conditions, those possibilities can interfere with each other. That is what makes quantum mechanics different from ordinary uncertainty. So in the next scene, we will slow down and look at superposition itself, what it means, what it does not mean, and why it should never be confused with magic. Superposition is one of the words that made quantum mechanics famous. It is also one of the words that made quantum mechanics easy to misuse. In popular culture, superposition is sometimes treated as a kind of permission slip for anything. A particle is everywhere. Reality is, whatever you choose. The universe waits for your thoughts. The cat is alive and dead because consciousness has not decided yet. These versions are memorable, but they are not careful physics. So let us slow down. Superposition is not magic. It is not positive thinking. It is not a mystical fog where all wishes are equally real. In quantum mechanics, superposition is a precise mathematical feature of quantum states. A quantum system can be described as a combination of different possible states, and under the right conditions, those different components can interfere with one another. That word, interfere, is the key. Interference is what makes superposition different from ordinary ignorance. Suppose you place a coin under a cup. You do not know whether it is heads or tails. Before you look, you might say, it could be heads or tails. But that is classical uncertainty. The coin has one definite state. You simply do not know it. Your ignorance is in your mind, not in the coin. Quantum superposition is different. An electron, photon, atom, or other quantum system can be placed in a state that is not merely one unknown classical possibility. It can behave as a genuine combination of alternatives. And because the alternatives are combined in the quantum state, they can produce interference effects. The double-slit experiment is the classic doorway into this idea. Imagine sending light toward a barrier with two narrow slits. On the other side is a screen. If light behaved only like tiny particles passing through one slit or the other, you might expect two bright bands on the screen, one behind each slit. But light can produce an interference pattern, bright and dark bands. A pattern created by waves overlapping. Where waves reinforce each other, the screen becomes brighter. Where waves cancel each other, it becomes darker. This is ordinary wave behavior. Water waves can do something similar. Sound waves can interfere. Light waves can interfere. But quantum mechanics becomes strange when we send particles one at a time. A photon, then another photon, then another. Each photon is detected as a localized spot on the screen. One small event, a click, a point, but after many photons are sent through the apparatus, the pattern builds up, not two simple bands, an interference pattern, the same kind of pattern associated with waves. This suggests that each photon is not simply choosing one slit in the ordinary classical sense. Its quantum state evolves as a superposition of alternatives associated with both paths. The photon is not a tiny marble, secretly passing through one slit, while we are merely ignorant, at least, not in the standard quantum description. The wave function contains both path alternatives, and those alternatives interfere. This is why superposition is not the same as not knowing. A hidden coin under a cup does not create interference between heads and tails. A quantum state can. That is the scientific bite, the part that cannot be replaced by ordinary uncertainty. Now, this does not mean we should imagine the photon as a tiny, glowing ball, physically smeared like jam across space. That picture can mislead us too. Quantum objects are not classical objects with blurry edges. The wave function is a mathematical object. It gives amplitudes. These amplitudes are used to calculate probabilities, and amplitudes can add, subtract, and interfere. The mathematics predicts the distribution of possible measurement outcomes. When a measurement occurs, we observe a definite result. One spot on a screen, one detector click, one outcome. But before measurement, the quantum state can evolve as a superposition. This is the structure that makes quantum predictions work. A superposition has coefficients, weights, amplitudes. These are not ordinary probabilities by themselves. They can be complex numbers, which means they carry phase information. Phase is what allows interference. Two amplitudes can combine constructively or destructively. They can reinforce or cancel. This is why quantum mechanics is not simply probability theory with smaller particles. It is probability with wave-like amplitudes. A world where alternatives can interfere before an outcome is measured. That is superposition without the mist. A mathematically defined combination of possible states whose amplitudes can interfere. Let us take another example. Spin. Quantum particles such as electrons have a property called spin. Spin is not exactly a tiny ball spinning around like a planet. The name is historical and intuitive, but imperfect. Spin is an intrinsic quantum property. When measured along a chosen axis, an electron may be found spin up or spin down. But before measurement, the electron can be in a superposition of spin up and spin down relative to that axis. This does not mean the electron is secretly spinning both ways like a confused toy. It means a quantum state is a combination of the basis states we call up and down. If you measure along that axis, you get one outcome with probabilities determined by the state. If you choose another axis, the same state can be expressed as a different combination of that axis's up and down states. This is important. Superposition depends on the basis we use to describe the system. A state that is definite in one basis can be a superposition in another. That sounds abstract, but it is central. It reminds us that superposition is not always a simple statement, like the particle is doing two ordinary things at once. It is a statement about how a quantum state is represented relative to possible measurements. In classical life, this feels strange. A cup is either on the table or not. A light is on or off. The door is open or closed. A cat is alive or dead. But quantum systems do not always fit those classical categories before measurement. The state can contain multiple possible outcomes in a way that affects future probabilities through interference. That is why the language becomes difficult. We borrow words from daily life here. They're up, down, wave, particle, alive, dead. But quantum mechanics is not daily life shrunk to a smaller size. It has its own structure. Superposition is part of that structure. The danger begins when we turn the word into a slogan. If we say, everything is in all states, until we look, we risk saying something too broad and too vague. If we say, consciousness chooses reality, we add a claim that the standard experiments do not require. If we say, the cat is literally alive and dead, in the same way a small object can be in spin, superposition, we ignore the role of macroscopic amplification, environment, decoherence, and interpretation. The careful version is quieter. Quantum systems can be prepared in superpositions. Those superpositions can produce interference. Measurement outcomes are probabilistic. When quantum systems interact with measuring devices and environments, the situation becomes more complex. Macroscopic superpositions become extremely fragile, and the question of how one definite outcome appears is the measurement problem. Schrödinger's cat uses superposition as a lever. The radioactive atom can be described as a superposition of decayed and not decayed, if isolated in the right way. The detector becomes correlated with that atom. The mechanism becomes correlated with the detector. The cat becomes correlated with the mechanism. If the whole sealed system is treated as a quantum system, evolving according to the wave function, the final state seems to combine two branches. Atom decayed, detector triggered, cat dead. Atom not decayed, detector not triggered, cat alive. This is not ordinary ignorance in the simple coin-under-cup sense. The formalism suggests an entangled superposition of alternatives. But this is exactly why the thought experiment is troubling. Because we do not observe cats as interference-producing alive and dead superpositions. A cat is not a photon passing through a double slit. A cat is a warm macroscopic system with enormous numbers of particles. It interacts internally and externally constantly. It becomes entangled with its environment in unimaginably many ways. This does not make quantum mechanics false. It makes the classical appearance of the world something to be explained. Decoherence will help us later. But first, we must understand the basic quantum idea clearly. Superposition is not a lack of decision in the human sense. It is not hesitation. It is not the universe being emotionally undecided. It is a linear combination of quantum states. Linear combination means that states can be added together with amplitudes. The Schrödinger equation allows such combinations to evolve. If one possible state is allowed and another possible state is allowed, then a combination of them is also a valid quantum state. This is called the superposition principle. It is one of the foundations of quantum mechanics. The superposition principle is why quantum theory is so powerful. It allows interference. It allows atomic orbitals. It allows quantum computing. It allows tunneling effects. It explains patterns that classical physics cannot. But it also creates the conceptual problem, because if superpositions are allowed, why do measurements give definite outcomes? And why do large objects not appear as visible superpositions? This is the path from the electron to the cat. The cat is not where superposition begins. The cat is where superposition becomes uncomfortable. Let us return to the double-slit experiment for a moment. If no which path information is available, interference can appear. The alternatives remain coherent. Coherence means that the relative phase relationships between components of the superposition are preserved. If which path information becomes available, interference disappears. It does not necessarily require a human watching. A detector that records which slit the photon went through can destroy the interference pattern. Why? Because the photon becomes correlated with the detector. The alternatives are no longer combined in the same coherent way for the observed system. Information about the path has leaked into the environment or apparatus. The interference becomes unavailable. This is already a small version of the measurement problem. Quantum alternatives can interfere when they remain coherent. When information about the alternatives becomes recorded in the wider world, interference is lost. That is the beginning of decoherence, the quiet leakage of phase relationships into the environment. The world does not wait for a mind. It interacts. Air molecules interact, photons interact, detectors interact, surfaces vibrate. Thermal radiation carries information away. The environment is always watching, in a physical sense, not consciously, not mystically, just by becoming correlated with systems. This is why macroscopic quantum superpositions are so delicate. To see interference with large objects, physicists must isolate them carefully, cool them, shield them, control their environment, reduce interactions. Experiments have shown quantum interference with increasingly large molecules in engineered systems. But the larger and warmer and more complex the system becomes, the harder it is to preserve coherence. A cat is about as unfriendly to coherence as a system can be: warm, wet, breathing, metabolizing, interacting, radiating heat, moving air, full of chemical processes. The cat is not a clean quantum laboratory object, and that is part of the point. Schrödinger chose a cat because it is obviously macroscopic and alive. The image forces us to confront the absurdity of extending microscopic superposition directly into ordinary language without explaining the transition. If we are careful, we can say the formal wave function of the entire sealed box may be written as a superposition of correlated alternatives. But saying the cat is alive and dead is a compressed phrase. It hides all the physics: the atom, the detector, the mechanism, entanglement, measurement, decoherence, interpretation. The phrase is famous, but the full meaning is not simple. This is why we should not treat Schrödinger's cat as proof that reality is whatever we decide. It proves no such thing. It shows that quantum theory challenges our classical categories. It shows that measurement is conceptually difficult. It shows that microscopic superpositions, when linked to macroscopic outcomes, create a paradox. It asks us to explain how definite outcomes arise. That is already strange enough. We do not need to add magic. Quantum mechanics is not less fascinating when we remove the mysticism. It becomes more fascinating, because the real theory is sharper than the slogan. A photon building an interference pattern, one detection at a time, is stranger than a motivational quote. An electron spin state changing its probabilities depending on measurement basis is stranger than vague cosmic uncertainty. A detector becoming entangled with a quantum system is stranger than saying consciousness creates reality. Decoherence spreading phase information into the environment is stranger than pretending the universe is waiting for a person to peek. The real physics does not need glitter. It has teeth. Soft teeth, perhaps, for tonight, but teeth. So when we say superposition, we will mean something specific. A quantum state that is a combination of possible states. A state whose amplitudes can interfere. A state whose measurement outcomes are probabilistic. A state that may become entangled with other systems. A state that becomes difficult to observe as a superposition when it interacts with a large environment. This careful definition prepares us for the cat, because the cat thought experiment depends on a chain. First, a microscopic quantum superposition, then a detector correlated with it, then a macroscopic mechanism, then a living outcome. Each link amplifies the quantum event. Each link makes the question harder. At what point, if any, does the superposition become a single result? That is the measurement problem, and to see it clearly, we need to examine the machinery inside the box, not as horror, not as drama, but as physics. The radioactive atom, the detector, the trigger, the poison mechanism, the sealed system, and the strange way a tiny quantum event can become a question about reality itself. The famous box is often described quickly: a cat, a radioactive atom, a detector, a poison mechanism, a sealed box. Then the phrase arrives: alive and dead. But if we move too quickly, we miss the real structure of the thought experiment. Schrödinger's cat is not only about the cat, it is about a chain. A tiny quantum event is connected to a macroscopic outcome. The important part is the link between scales: microscopic, detector, machine, living system, observer. Each part of the chain raises a question: where does quantum possibility become definite fact? Let us begin with the radioactive atom. Radioactive decay is a quantum process. An unstable atomic nucleus can decay, releasing radiation, but quantum mechanics does not generally predict the exact moment when one particular nucleus will decay. Instead, it gives probabilities. For a large sample of radioactive atoms, the statistics are very reliable. If a material has a half-life of 1 hour, then after 1 hour, about half of a large number of nuclei will have decayed. But for one individual atom, the theory gives a probability. It may decay during the interval, or it may not. There is no ordinary hidden clock in the usual quantum description, ticking toward a predetermined second. The decay is treated as fundamentally This is already different from classical intuition. In classical physics, if something happens unpredictably, we often imagine that we simply lack enough information. A coin toss seems random, but if we knew the exact force, angle, air resistance, rotation, and collision details, we could, in principle, predict the result. The randomness comes from complexity and ignorance. Radioactive decay is different in standard quantum mechanics. The probability is not merely a practical limitation, it is built into the theory. The nucleus is described by a quantum state. That state evolves. During a given time interval, there is an amplitude for decay and an amplitude for no decay. If the system remains isolated, the quantum description can involve a superposition of decayed and not decayed components. This is the first step in the box. A microscopic system with two possible outcomes: decay, no decay. Now add a detector. A detector is a physical device designed to register radiation. In the usual versions of the thought experiment, this might be a Geiger counter or something similar. If the atom decays, the detector responds. If the atom does not decay, the detector remains silent. The detector converts a microscopic event into a macroscopic signal. This conversion is crucial. A tiny emission from a nucleus becomes an electrical pulse. A small quantum event becomes something a machine can amplify. The detector does not need to understand quantum mechanics. It simply interacts physically with the emitted radiation. If radiation enters the detector, it causes ionization or another measurable effect. Electrons move. A current changes. A click may be produced. A circuit may respond. A record may be created. Already, the quantum event is no longer isolated. It has become correlated with a larger system. If the atom decayed, the detector is in a triggered state. If the atom did not decay, the detector is in an untriggered state. Quantum mechanically, if the atom was in a superposition and the detector is included in the description, the combined state becomes entangled. Entanglement means the state of one part cannot be described independently of the other. The atom and detector are now linked. Decayed goes with detector triggered. Not decayed goes with detector silent. This is not merely two separate facts listed side by side. It is a correlated quantum state, a joint description. The detector has become part of the measurement chain. Now add the mechanism. In Schrödinger's thought experiment, the detector is connected to a device that releases poison if the decay is detected. This is the most dramatic part of the story, and the part most likely to distract us. But scientifically, we should see it as amplification. The mechanism takes the detector signal and converts it into a large-scale consequence. A microscopic decay event affects a macroscopic system. The point is not the poison itself. The point is that a small quantum event becomes linked to an outcome that is unmistakably classical in ordinary language. The cat is alive, or the cat is dead. These are not subtle detector readings. They are macroscopic states. They involve a huge number of atoms, biochemical processes, heat, motion, breathing, circulation, neural activity, and interaction with the environment inside the box. Schrödinger chose a cat because it forces the issue. A detector needle in two possible positions might already be puzzling. A living cat makes the puzzle impossible to ignore. You cannot casually say a cat is both alive and dead without feeling that something has gone wrong in the way we are speaking. That discomfort is exactly the purpose of the thought experiment. The setup is designed so that one quantum event controls the fate of a macroscopic object. Atom decays, detector triggers. Mechanism activates. Cat dies. Atom does not decay. Detector does not trigger. Mechanism stays inactive. Cat lives. From outside the sealed box, before opening, the observer does not know which chain occurred. In ordinary classical uncertainty, that would be simple. The cat is either alive or dead. We just do not know which. Like a coin hidden under a cup, heads or tails, unknown to us, but definite. Schrödinger's point was that quantum mechanics seems to say something more troubling if applied to the entire closed system. If the atom is in a superposition of decayed and not decayed, and if the detector, mechanism, and cat become entangled with that atom, then the wave function of the whole box seems to contain both branches. One branch with decay, triggered detector, activated mechanism, dead cat. Another branch with no decay, silent detector, inactive mechanism, living cat. The cat is not introduced because cats are quantum in a special mystical way. The cat is introduced because the quantum event has been amplified. The cat is the endpoint of a chain, and that chain forces us to ask what the wave function means. Is the wave function a complete description of reality? If yes, then the superposed state of the sealed box seems to be real in some sense. But if the cat is never observed in such a superposition, why not? Does the wave function collapse at some point? If it collapses, when the detector registers the particle, when the mechanism responds, when the cat is affected, when a human opens the box, or does collapse never happen, with the different branches continuing in some larger quantum state? These questions are why the thought experiment matters. The box is a laboratory for interpretation, not a real proposed animal experiment, not a practical apparatus to build, a conceptual machine, a device for making the measurement problem visible. It takes the abstract tension inside quantum theory and places it into an image that cannot be ignored. A box you cannot see into, a quantum event you cannot predict exactly, a detector that amplifies the event, a mechanism that makes the result macroscopic, a cat that represents ordinary reality, an observer outside, waiting. The sealed box matters because it hides the outcome from the observer. But hiding is not the same as isolating perfectly from a physics point of view. This is a subtle point. In the thought experiment, the box is sealed so the observer does not know the result. But inside the box, the cat, detector mechanism, air molecules, thermal radiation, and all internal components interact constantly. The system is not simple. Even if the outside observer is ignorant, the inside of the box is full of physical interaction. This distinction is crucial. There is a difference between not knowing a result and it being in a coherent quantum superposition. For a coin under a cup, not knowing is ordinary ignorance. For a quantum system, superposition allows interference. For the cat, maintaining coherent interference between alive and dead branches would be fantastically difficult. The cat and apparatus would almost immediately become entangled with countless environmental degrees of freedom. Air molecules would scatter. Thermal photons would carry information. Mechanical vibrations would spread. Chemical states would differ. The two branches would become effectively unable to interfere. This is decoherence beginning to enter the story. But before we go fully into decoherence, we should stay with the chain, because the measurement chain is the skeleton of the paradox: atom, detector mechanism, cat, observer. Each link asks whether measurement has happened yet. The radioactive atom alone can be described as a quantum superposition. When the detector interacts with it, many physicists would already say a measurement-like process has occurred. A record has been created. The microscopic event has been amplified. But if we treat the detector itself quantum mechanically, then the detector becomes entangled rather than magically outside the theory. This is what makes measurement hard. A detector is made of atoms too. A measuring device is a physical system. It does not live in a separate classical universe. If quantum mechanics applies to atoms and detectors are made of atoms, why not apply quantum mechanics to detectors? But if we do, superposition spreads into the apparatus, then into the mechanism, then into the cat. That is the change Schrödinger wanted us to notice. The measurement problem is not solved by simply saying a measurement happens. We have to explain what that means physically. Does measurement require irreversibility, a macroscopic record, environmental decoherence, conscious observation, a fundamental collapse law, a branching universe? Different interpretations answer differently, but the thought experiment forces every answer to show its work. The poison mechanism, grim as it sounds, is therefore not the heart of the story. It is a scale amplifier, a translation device. It translates a nuclear event into a macroscopic distinction, alive or dead. In real quantum experiments, amplification is common. A single photon can trigger an avalanche of electrons in a detector. A tiny ionization event can become a voltage pulse. A microscopic interaction can become a visible spot on a screen. Measurement devices are built to amplify. They turn small quantum events into stable records. A dot, a click, a number, a trace. a photographic grain, a digital bit. The CAD experiment takes this familiar amplification and makes it extreme. Instead of a dot on a screen, the outcome is the state of a cat. This is why the setup feels unsettling. It connects the delicate quantum world to the heavy classical world in one continuous chain. One of the most important lessons is that measurement is physical. It is not merely looking. It is not simply awareness. It is interaction, correlation, amplification, and record formation. When a detector measures a particle, the detector changes. When a screen detects a photon, the screen changes. When a device stores a result, matter changes. Measurement leaves traces, and traces are physical. This connects Schrödinger's cat to the arrow of time we explored in the previous video. A measurement record is usually irreversible for all practical purposes. A detector click spreads information into a large number of degrees of freedom. A spot on a screen is a stable mark. A digital record is a physical state. The measurement chain is entangled with entropy, decoherence, and irreversibility. Quantum mechanics and thermodynamics meet inside the apparatus. This is one reason the foundations of quantum theory are so rich. A measurement is not just a mathematical update. In the lab, it is a physical process. Energy moves, materials change, signals amplify, information becomes recorded. The box is not just a box, it is a small universe of interactions. And the cat, again, is not there to make the story theatrical. It is there to make the consequences impossible to dismiss. If quantum theory treats the entire box as a superposition, then our ordinary categories strain. If the box has a definite outcome before we open it, we must explain how that outcome arises from the quantum formalism. If the outcome is only definite relative to some observer or branch or record, we must say what that means. If the wave function collapses objectively, we must say when and why. This is not a question that slogans can answer. It is a question that interpretations of quantum mechanics try to answer. At this point, we can say something careful. In the real world, a macroscopic cat in a box would not remain in a neat, coherent superposition of alive and dead states in any experimentally accessible way. Decoherence would happen extraordinarily fast. The two alternatives would become entangled with the environment. Interference between them would become effectively impossible to observe. So the popular image of a visibly half-alive, half-dead cat is misleading. The cat is not glowing in a mystical blend. It is part of a vast, entangled physical system. And the question is how that system relates to the single outcome we experience. This is the quieter, more accurate version, less flashy, more powerful. The cat does not prove that consciousness creates reality. It does not prove that anything you imagine exists. It does not prove that all possibilities are equally available to your mind. It shows that quantum theory, when connected to measurement, forces us to ask what counts as a physical outcome that is already extraordinary. A radioactive atom in a sealed box becomes a doorway to the foundations of reality, not because the atom is magical, because the theory is precise enough to reveal where our classical language fails: decay and no decay, triggered and not triggered, alive and dead, superposition and outcome, wave function and observation. The chain inside the box ties them together, and once we understand that chain, the next question becomes unavoidable. What is this wave function that seems to contain the alternatives? Is it a real physical object? Is it a mathematical tool for predicting probabilities? Is it knowledge? Is it information? Is it something else? To understand Schrödinger's cat, we now need to look directly at the wave function and the measurement problem, the place where the mathematics works beautifully and the meaning becomes beautifully difficult. The wave function is one of the central objects in quantum mechanics. It is also one of the most debated. Mathematically, the wave function lets physicists calculate probabilities. If we know the wave function of a quantum system, we can predict the probabilities of different measurement outcomes, where a particle may be detected, what spin result may be found, whether an atom may decay during a certain time interval, which energy level an electron may occupy. The wave function is not usually something we see directly. We do not open a box and look at a wave function with our eyes. We observe outcomes, detector clicks, spots on a screen, energy levels, tracks, counts, readings. The wave function is the mathematical structure used to predict the pattern of those outcomes. But the difficult question is this: what is the wave function? Is it a real physical thing? Is it a complete description of reality? Is it only a tool for calculating what we know? Is it information? Is it something objective in the world, or something connected to an observer's knowledge? Different interpretations of quantum mechanics answer these questions differently, and this is where the measurement problem begins to sharpen. In ordinary quantum theory, the wave function evolves according to Schrödinger's equation when the system is not being measured. This evolution is smooth, continuous, deterministic. If you know the wave function now, the equation tells you how it changes. but measurement appears to be different. When we measure, we get one definite result. A particle is detected here. A spin is found up, a detector clicks, an atom has decayed. Before measurement, the wave function may contain a superposition of possible outcomes. After measurement, we observe one outcome. The question is, what happened? This is the measurement problem. The mathematics seems to contain two kinds of evolution. First, smooth wave function evolution. Second, measurement giving a definite result. If the wave function evolves smoothly, why do we see only one outcome? If the wave function collapses, what causes the collapse? Is collapse a real physical process, or is collapse only an update in our knowledge when we learn the result? The word collapse is famous, but it can be misleading. It suggests a physical wave suddenly shrinking, like a balloon snapping into a point. But depending on the interpretation, collapse may not be a physical event at all. It may be a rule for updating probabilities after measurement, or it may be a real dynamical process, or it may be unnecessary if all outcomes continue in different branches. This is why we must be careful with language. The experimental predictions of quantum mechanics are extremely precise, but the meaning of the wave function is still interpreted in different ways. Let us take a simple example. A quantum particle is sent toward a screen. Before detection, its wave function may be spread over a region. The theory gives probabilities for where the particle might be detected. When the particle is detected, we see one spot, not a faint smear everywhere. One localized event. If we repeat the experiment many times with identically prepared particles, the spots build up a pattern. The wave function is not usually something we see directly. We do not open a box and look at it with our eyes. We observe outcomes. Detector clicks, spots on a screen, tracks, readings. The wave function is the structure used to predict the pattern of those outcomes. But the difficult question is this. What is it? Is it a real physical thing? A complete description of reality? Or just a tool for calculating what we know? During the waiting time, the atom may be described as a superposition of decayed and not decayed. If it decays, the detector triggers. If it does not, the detector remains silent. If we include the detector in the quantum description, the atom and detector become entangled. The combined wave function includes correlated alternatives. Decay with trigger detector. No decay with silent detector? Then the mechanism and cat become part of the chain. The wave function of the box seems to contain two branches. A live cat, dead cat. Not because the cat is mystical, because quantum theory, applied universally, seems to spread the superposition through the measurement chain. The difficulty is not in calculating probabilities. The difficulty is in saying what the calculation means. From the outside, before opening the box, we do not know the result. But is the cat merely unknown, like a hidden coin? Or is the whole box genuinely in a superposed quantum state? If it is superposed, why do we never observe interference between alive and dead cat branches? If it is not superposed, when did the superposition end? This is the heart of the paradox. The measurement problem is not solved by saying, we looked, because looking is a physical process too. Light interacts with the box. Photons enter eyes or a camera. Signals travel through nerves or electronics. Records form. The observer is part of the physical world. If everything is made of quantum systems, then the observer is not magically outside the theory. This is why measurement is so difficult to define. In the laboratory, measurement often means a system becomes correlated with a device in a stable, irreversible way. A detector records a click. A screen records a spot. A sensor stores a bit. A pointer moves. A trace remains. The outcome becomes available to the wider world. But the boundary between quantum system and classical apparatus is not always fundamental. It is often practical. We treat the small system quantum mechanically and the large apparatus classically because that works extremely well for predictions. But in principle, the apparatus is also made of atoms. So, should we describe the whole apparatus with a wave function? If yes, the superposition spreads. If no, we need to say where and why the quantum description stops. This is the measurement cut, the line between the quantum system and the classical measuring device. In the Copenhagen tradition, this cut is often treated as necessary for describing experiments. We use classical language to describe the apparatus and outcomes. The quantum system is described by a wave function. The measurement connects the two. This approach is practical and successful. It tells physicists how to calculate and interpret experiments. But it can feel incomplete if we ask for a fully physical story of what happens during measurement. Where exactly is the cut? Is it movable? Does it represent a real boundary in nature, or only a boundary in our description? Schrödinger's cat pushes this question by making the apparatus large. If the atom is quantum and the detector is classical, perhaps the problem seems manageable. But if the detector, mechanism, and cat are all made of quantum matter, the cut is harder to place. The cat forces the cut into the open. This is why it remains powerful. It asks whether quantum mechanics can describe the whole measurement process without an unclear boundary. Some interpretations say yes, some say no, some change the wave function's meaning, some change the dynamics, some accept branching, some add hidden variables, some emphasize information. But all must face the measurement problem. Let us look more carefully at what a measurement does physically. A measurement creates correlation. If the particle has one property, the device enters one state. If the particle has another property, the device enters another state. The device becomes a record of the system. In quantum mechanics, this correlation can become entanglement. The system and apparatus are described together. Their states are linked. For a simple example, imagine a quantum system that can be in state A or state B. A detector begins in a ready state. If the system is A, the detector moves to detector state A. If the system is B, the detector moves to detector state B. If the system begins in a superposition of A and B, then after interaction, the combined state may become a superposition of system A with detector A and system B with detector B. This is measurement-like entanglement. The detector has not merely observed from outside, it has become physically correlated with the system. Now add the environment. The detector is not isolated. It interacts with air, photons, vibrations, thermal radiation, support structures, electronics, and surrounding matter. These interactions spread information about the detector state into the environment. The environment becomes correlated to. This is decoherence. The relative phase information between alternatives becomes dispersed into the environment. Interference between macroscopically different outcomes becomes effectively impossible to observe. This explains why we see stable classical outcomes. A pointer points one way. A detector has one reading. A cat is alive or dead, not a visible mixture. But decoherence by itself does not necessarily select one outcome in every interpretation. It explains why branches no longer interfere. It explains why the world appears classical. It explains why macroscopic superpositions are hidden. But whether one branch becomes the only real outcome, or whether all branches continue, or whether collapse occurs dynamically, depends on interpretation. This is why decoherence is powerful, but not the entire philosophical ending. It solves much of the practical puzzle of why the classical world appears classical. It does not automatically tell everyone what the wave function ultimately is. That is the delicate boundary. Physics has tools: mathematics, experiments, decoherence theory, interpretations. But we should not pretend the foundations are simpler than they are. Schrödinger's cat survives because the question is genuinely deep. Now, there is another common confusion. People sometimes think measurement means a human mind becomes aware. This is not how most physicists use the term in practice. A measurement can be performed by a detector left running in an empty laboratory. The detector can store data. The data can be read later. The physical outcome is recorded whether or not a person was watching at the moment. Human consciousness is not required for a Geiger counter to click. It is not required for a photographic plate to change. It is not required for a bubble chamber to leave a particle track. What matters physically is interaction and record formation. Consciousness may be philosophically interesting, but it is not needed to explain ordinary quantum measurements. This is one of the most important lines for our video. Observation is not magic attention. Observation is physical interaction that produces a record. The world does not wait for us to look. It interacts constantly. When a dust grain floats in sunlight, photons scatter from it. When a molecule hits a surface, momentum is exchanged. When a detector absorbs a particle, a signal forms. When a cat breathes in a box, air molecules, heat, and internal biological processes create a roaring storm of correlations. The environment is an enormous measuring apparatus, not conscious, not intentional, just physical. This is why macroscopic superpositions decohere so quickly. A cat-sized object cannot remain quantum coherent in the same way an isolated electron can. The environment is always stealing phase information, always spreading correlations, always making interference between large alternatives unavailable. This brings us closer to a modern view. The transition from quantum to classical is not usually a sharp, magical moment. It is a process. A quantum system interacts with a measuring device. The device amplifies the difference. The environment becomes entangled with the outcome. Coherence between alternatives becomes practically lost. A stable record appears. The world looks classical, but the interpretive question remains. Did the wave function truly collapse? Did one outcome become real and the others vanish? Did all outcomes continue in separate branches? Was the wave function only a tool for our knowledge? Was there a hidden variable determining the result? These questions belong to interpretations. The mathematics tells us what probabilities to expect. The interpretations tell different stories about what the mathematics means. For Schrödinger's cat, this matters deeply. In a collapse interpretation, the cat may become definitely alive or dead when some physical collapse occurs. In a many-worlds interpretation, the combined wave function branches into non-interacting alternatives, one with a live cat and one with a dead cat. In a Copenhagen-like view, the theory may not assign a classical outcome until measurement is defined in the experimental context. In objective collapse models, the wave function collapse is a real physical process that becomes more likely for large systems. Each view handles the box differently. None of this should be turned into a slogan. The important point is that the cat is not a simple fact. It is a question aimed at the foundations, a question about wave functions, measurement, outcomes, reality, and the boundary between quantum and classical description. If this feels difficult, that is appropriate. The measurement problem is difficult. It is not difficult because people explain it badly, though they often do. It is difficult because quantum mechanics forces us to separate calculation from interpretation. The calculations work, the predictions work, the experiments work, but the meaning still invites debate. That is rare and beautiful. A theory can be astonishingly successful and still philosophically sharp. Quantum mechanics is like a machine that produces correct numbers while quietly asking what those numbers are about. Schrödinger's cat is one of the questions printed on the side of the machine. Tonight, we do not need to choose a final interpretation yet. We only need to understand the problem clearly. The wave function describes possible outcomes through amplitudes. It evolves smoothly when isolated. Measurements produce definite outcomes. Measurement involves physical correlation, amplification, and records. The boundary between quantum superposition and classical result is the hard part. Schrödinger's cat places that boundary inside a sealed box. The wave function can be written, the probabilities can be calculated, but the meaning of the cat state depends on what we believe the wave function represents. This is the quiet center of the paradox. Not the cat alone, not the poison, not the observer's eyes, but the question, what is a measurement? And as we move forward, the next piece becomes essential. Why is a cat not like an electron? Why can tiny systems show superposition and interference, while large warm objects appear definite? The answer begins with scale, complexity, environment, and decoherence. The place where the quantum world does not disappear, but becomes hidden beneath the classical world we know. An electron can be placed in a delicate quantum state. A photon can pass through an experiment and produce interference. An atom can be cooled, isolated, trapped, and measured with extraordinary care. But a cat is not like an electron. This sounds obvious. A cat is larger, warmer, more complex, alive, made of an enormous number of atoms. But, in quantum mechanics, this obvious difference hides a deep question. If everything is made of quantum matter, why does the large world not look quantum? Why do electrons show interference, while cats do not? Why can small systems remain in carefully prepared superpositions, while macroscopic objects appear definite? Here, there, alive, dead, hot, cold, broken, whole. The answer begins with scale. An electron is simple compared with a cat. Not simple in the sense that quantum theory is easy, but simple in the sense that it has relatively few relevant degrees of freedom. A degree of freedom is a way a system can vary or store information, position, momentum, spin, energy level. A single electron can be described by a small set of quantum properties. It can be isolated from the environment with careful experimental design. It can be shielded, prepared, controlled, measured. The cleaner the isolation, the longer its quantum coherence can survive. Coherence is the preservation of the phase relationships in a quantum superposition. Without coherence, interference disappears. So for an electron, photon, atom, or small molecule, physicists can sometimes create conditions where coherence remains long enough to observe quantum effects. They use vacuum chambers, low temperatures, careful shielding, precise lasers, magnetic traps, sensitive detectors. The laboratory becomes a quiet shelter for fragile quantum behavior. A cat is the opposite of that. A cat is not isolated. Even inside a box, a cat is interacting constantly with air molecules, with thermal radiation, with the floor of the box, with its own body, with chemical processes, with sound waves, with internal heat, with metabolism, with breathing, with countless microscopic changes happening every instant. A cat is not a single clean quantum system in practice. It is a vast, warm, wet, noisy collection of quantum systems interacting with each other and with the environment. The number of particles involved is enormous. Atoms in tissues, molecules in cells, water molecules, proteins, ions, neurons, blood, air, radiation. Each part interacts with many others. Every interaction can carry information. Every scattering event can create correlations. Every thermal photon can leak a tiny trace of the system's state. This matters because quantum superpositions are fragile when the alternatives are macroscopically different. A superposition of an electron spin up and spin down can be preserved under the right conditions. A superposition of a cat alive and dead would require maintaining coherence between two vastly different macroscopic states. The living cat branch and the dead cat branch would differ in enormous numbers of degrees of freedom. Biochemistry, motion, heat flow, air composition, radiation, internal states, environmental correlations. To observe interference between those branches, the phase relationship between them would need to remain available. But the environment would almost instantly become entangled with the difference. Information would spread everywhere. This spreading is decoherence. Decoherence is not the quantum world turning off. It is the loss of observable interference between components of a superposition because the system becomes entangled with its environment. The alternatives still exist in the mathematical description, depending on interpretation, but they no longer interfere in any practical way. For macroscopic systems, decoherence can happen extremely fast. So fast that the classical world appears stable and definite. This is why the cat does not behave like a single electron. Not because quantum mechanics stops applying, but because quantum coherence becomes effectively inaccessible. The cat is too open, too warm, too complex, too entangled with everything around it. This is one of the most important points in the entire story. The classical world is not separate from quantum mechanics. It emerges from quantum mechanics under conditions where coherence is lost to the environment. The quantum does not vanish. It becomes hidden in correlations too complex to recover. Think of a tiny ripple on a perfectly still pond. If the pond is calm, you can see the ripple clearly. You can watch it move. You can study its shape. Now imagine the same ripple in a stormy ocean. Waves crash, wind blows, foam moves, currents mix. The ripple still has physics, but it is no longer visible as a clean pattern. It has been swallowed by the larger environment. Quantum coherence is similar. In a clean, isolated system, the pattern can be seen. In a large, warm environment, the pattern is rapidly dispersed. This is not a perfect analogy, but it helps. A cat-sized superposition would require the pond of reality to remain impossibly still, but the cat is its own storm. Now consider thermal radiation. Any warm object emits radiation. A cat, being warm, emits infrared photons. Those photons carry information about the cat's state, its position, shape, temperature, surface, motion. They leave the system and travel outward. Even in a sealed box, radiation interacts with the walls. Air molecules collide with the cat and with the box. The environment becomes correlated with the cat's macroscopic condition. If there were two branches, alive and dead, the environment would rapidly carry different information about each one. Those environmental records make interference between the branches effectively impossible. The superposition becomes decoherent. This is why macroscopic objects look classical. A chair does not appear in two places at once because it is constantly being monitored by its environment. Photons scatter off it, air molecules hit it, vibrations pass through it, thermal radiation leaves it, dust settles on it. The environment is making records all the time, not conscious records. Physical records, correlations, traces, a tiny piece of information leaking into countless. For an electron in a lab, we can reduce such interactions. For a chair, a cat, or a cup of coffee, we cannot. The environment is too involved. This is why the phrase "the observer collapses" the wave function can mislead people. In real physical systems, the environment often does much of the work long before a human observer arrives. A human opening the box is not the first interaction. The cat has already interacted with air, photons, heat, mechanisms, and internal processes. The detector has interacted with the atom. The mechanism has interacted with the detector. The box has interacted with its contents. The system has become a dense web of correlations. By the time a person opens a box, the branches, if described quantum mechanically, are no longer capable of ordinary interference. The outcome appears classical. The observer reads a record that has already been physically formed. This does not mean the measurement problem disappears completely. Decoherence explains why interference becomes unobservable. It explains why certain states become stable, classical-looking alternatives. It explains why macroscopic superpositions are not seen directly. But decoherence alone does not force every interpretation to say exactly one outcome exists. In many worlds, decoherence explains why branches stop interfering and appear as separate worlds. In collapse theories, decoherence may accompany but not replace real collapse. In Copenhagen-like views, decoherence helps explain why classical descriptions are effective. So decoherence is not the entire philosophical answer, but it is an essential physical mechanism. Without it, the cat paradox floats too freely. With it, we understand why the cat is not like an electron. Now, let us think about isolation. Quantum experiments often fight against the environment. To preserve superposition, physicists isolate systems. They remove air, cool the apparatus, reduce noise, shield from stray radiation, use lasers to control motion, use traps to hold atoms, use superconducting circuits at extremely low temperatures. The goal is to prevent unwanted interactions from carrying away information. Because once the information leaks into the environment, coherence is lost. This is why quantum computers are so difficult to build. Qubits must remain coherent long enough to perform calculations. But every qubit is vulnerable to heat vibration, electromagnetic noise, material defects, cosmic rays, unwanted coupling to the environment. The same principle that prevents cats from showing visible superpositions also makes quantum technology delicate. The environment is always trying to listen. Again, not consciously, physically. A qubit is like a whisper in a crowded room. To hear it, you must make the room quiet. A cat is not a whisper. A cat is a thunderstorm of interactions. This is a scale problem. The larger the system, the more ways it can become entangled with its environment, the more degrees of freedom it has, the more places information can leak. The more thermal motion it contains, the harder it is to maintain phase relationships. The more complex it becomes, the faster coherence disappears. This is why we do not see quantum interference in daily life. It is not because daily objects are not made of quantum matter. They are. It is because the quantum phases needed for visible interference are dispersed into the environment far too quickly. The classical world is a quantum world that has decay. That sentence is worth holding for a moment. The classical world is a quantum world that has decay. A table is made of atoms. A clock is made of atoms. A detector is made of atoms. A cat is made of atoms. But their collective states are constantly correlated with their environments. The delicate quantum alternatives that might interfere are effectively separated. The world looks definite, stable, classical, not because quantum mechanics failed, but because it worked together with the environment. Now, there is another way to think about the cat. A quantum superposition is not just a list of possibilities. It is a coherent combination that can, in principle, produce interference. If no interference can ever be observed between the alternatives, the situation begins to look like an ordinary mixture for practical purposes. A mixture means we have probabilities over alternatives, but no usable phase relationship between them. Alive with some probability, dead with some probability, but no interference between alive and dead states. Decoherence turns coherent superpositions into effective mixtures when we ignore the environment. This is a technical statement, but it is central. The full system, including environment, may still be described by a quantum state. But if we look only at the cat and apparatus, and do not track the enormous environment, the system behaves as though it is in a classical probabilistic mixture. This is why decoherence is often described as explaining the appearance of classical reality. It does not make quantum theory less strange. It shows where the strangeness goes. Into correlations, into environmental degrees of freedom, into information spread too widely to recover. The cat is not protected from this. The cat is an engine of decoherence. This is also why the thought experiment is not something you can simply build in the naive form and expect to find a half-dead, half-live cat. A real cat is too large and too connected. The only possible outcomes we expect to observe are classical ones, alive or dead, not a visibly coherent combination. The paradox is about the formal description and the interpretation of measurement, not about seeing a ghostly cat blend. This distinction keeps the science clean, and it protects us from the common fantasy version. The cat is not a mystical creature suspended by human attention. It is a macroscopic system whose quantum coherence between drastically different outcomes would be destroyed by environmental entanglement extremely quickly. That may be less poetic at first, but it is far more interesting, because it tells us something real about the boundary between quantum and classical. There is no simple size at which quantum mechanics turns off. There is no magic line where particles become objects and quantum rules retire. Instead, there is a gradual and extremely rapid process of decoherence, a process controlled by interaction, complexity, temperature, and environment. Small systems can show quantum interference if isolated. Large systems usually cannot, because they are never isolated enough. This is why physicists can put larger and larger molecules into interference experiments, but only with extraordinary care. They are testing how far quantum behavior can be pushed. How large can a system be and still show coherence? How complex can it be? How well can it be isolated? These experiments are not games. They probe the quantum classical boundary. They ask whether quantum mechanics continues to hold at larger scales. So far, quantum mechanics remains astonishingly successful, But the practical difficulty rises sharply with size and complexity. The cat remains safely beyond any ordinary coherent experiment, not because it is outside physics, because it is too physically involved with the world. A cat has no quiet quantum privacy. Every breath is a measurement-like interaction. Every emitted photon is a trace. Every warm surface leaks information. Every internal process multiplies correlations. The cat is constantly becoming classical to its environment. This helps explain why the thought experiment still matters. It is not only asking whether cats can be in superposition, it is asking how classical definiteness emerges from quantum rules. The answer begins with decoherence, and in the next scene, we will look at decoherence directly. How the environment takes delicate quantum phase information and spreads it outward. How interference disappears. How a world of possibilities becomes, for all practical purposes, a world of stable outcomes. The cat is not like an electron, and decoherence is one of the main reasons why. Decoherence is one of the most important ideas for understanding Schrödinger's cat. It does not make the paradox disappear completely, but it changes the shape of the problem. It shows why the classical world appears so definite, why tables, chairs, detectors, and cats do not seem to float in visible quantum superpositions, and why the environment is not a passive background. The environment is part of the story. To understand decoherence, return for a moment to superposition. A quantum system in superposition has components with phase relationships. Those phase relationships allow interference. In a double-slit experiment, if the alternatives remain coherent, an interference pattern can appear. The two paths can combine like waves. The amplitudes can reinforce or cancel. But if information about which path leaks into the environment, the interference disappears. Not necessarily because a human looked, not because a mind entered the room, because the system became entangled with something else. A detector, an air molecule, a photon, a vibrating surface, a thermal environment. When the environment carries information about the alternatives stop interfering in any accessible way. That loss of accessible interference is The word can sound technical, but the core idea is calm. Coherence means the parts of a quantum superposition maintain their phase relationship. Decoherence means that relationship becomes dispersed into the environment, not destroyed like a light being switched off. Dispersed, spread out, hidden in correlations among many degrees of freedom. Imagine a perfectly clear ripple pattern on still water. Two waves overlap. They create bright ridges and quiet troughs. Now imagine that the water is connected to countless other ripples, currents, splashes, and disturbances. The original pattern becomes impossible to see. The information has not simply vanished into nothing. It has become mixed into too many other motions. Quantum decoherence is not exactly water waves, but the feeling is similar. A clean pattern becomes unavailable when it becomes entangled with a large environment. The environment does not need to be large in size. It needs to have enough degrees of freedom to carry away phase information. In a laboratory, even a few uncontrolled interactions can matter. A stray photon can reveal which path a particle took. A molecule of air can scatter from a system. A tiny vibration can couple to an apparatus. Thermal radiation can carry information outward. Each interaction is small, but each can leak information, and once that information leaves the system, interference becomes harder to observe. For macroscopic objects, the leakage is enormous. A dust grain in sunlight scatters photons constantly. Each scattered photon carries some information about the dust grain's position. A chair in a room interacts with air molecules, light, heat, radiation, and vibrations. A cat interacts with everything inside and around it, including its own internal environment. These interactions happen unimaginably fast. They make macroscopic superpositions, decay almost instantly. This is why classical reality appears stable. The environment is always taking notes, not conscious notes, physical notes, correlations, records, tiny pieces of information spread across the world. A photon bouncing off an object becomes correlated with that object's position. An air molecule colliding with a surface becomes correlated with that surface. Thermal radiation leaving a warm body becomes correlated with its temperature and shape. The environment becomes a witness. Again, not a mind, a physical witness, a system that carries information. This phrase, environment, as witness, is useful. It means the world around an object is constantly recording information about it through interaction. The result is that certain states become stable and classical looking. A pointer aiming left or right, a cat alive or dead, a spot on a screen, a bit in memory. These states are robust because their information spreads into the environment. They can be copied, recorded, observed by many systems. They do not remain delicate, coherent combinations. This is part of why we experience a shared classical world. You and I can both see the same table because light scatters from it into the environment. Many observers can gather information about it. The table's position is redundantly recorded in photons, air molecules, and surrounding interactions. This redundancy makes the classical state objective in practice, not because quantum mechanics has vanished, because the environment has selected stable records. The technical term sometimes used here is quantum Darwinism. It is an extension of decoherence theory. The idea is that certain states survive interaction with the environment better because they can be redundantly recorded. These are called pointer states. They are the states that remain stable enough to be observed classically. A pointer on a measuring device points to one result. The environment spreads information about that pointer state. Many observers can read the same result. The fragile superpositions between macroscopically different pointer states become inaccessible. We do not need to go too deeply into quantum Darwinism tonight, but it gives us a useful image. The classical world is not chosen by a magical observer. It is carved out by interaction with the environment. Stable information survives. Delicate phase relationships disappear into the surroundings. Now return to Schrödinger's cat. Inside the box, suppose the atom becomes correlated with the detector. The detector becomes correlated with the mechanism. The mechanism becomes correlated with the cat. The cat becomes correlated with air molecules, photons, thermal radiation, and internal biological processes. The alive and dead alternatives are not small differences. They are enormous macroscopic differences. They involve different patterns of heat, motion, chemistry, and structure. The environment inside the box very quickly becomes different depending on the alternative. If the cat is alive, the internal environment has one pattern. If the cat is dead, another. Air molecules scatter differently. Thermal photons differ. Chemical processes differ. The branches become entangled with distinct environmental states. The phase relationship between those alternatives becomes effectively impossible to access. The superposition has decayed. This is why we do not expect to open the box and see an interference pattern between alive and dead. We see a classical outcome, alive or dead. The possibilities no longer interfere in the way small, coherent quantum alternatives can. Decoherence explains why the cat behaves classically for all practical purposes. But we should say this carefully. Decoherence does not necessarily say which single outcome is ultimately real. That depends on interpretation. In the many worlds interpretation, decoherence explains why branches stop interfering and appear separate. In collapse interpretations, decoherence explains why macroscopic alternatives are stable, but collapse selects one. In Copenhagen-style approaches, decoherence supports the practical use of classical outcomes and apparatus. Different interpretations use decoherence differently, but nearly everyone agrees that decoherence is physically important. It is not optional decoration. It is one of the main reasons the quantum world becomes classical-looking. The phrase "for all practical purposes" often appears here. For all practical purposes, interference between macroscopic branches is gone. For all practical purposes, the cat is in a definite state. For all practical purposes, the apparatus has a stable outcome. But some physicists are not satisfied with "for all practical purposes." They ask whether the problem is solved, in principle. If the full wave function still contains multiple branches, why do we experience one? If collapse occurs, what physical law causes it? If the wave function is only knowledge, whose knowledge and what physical reality underlies it? Decoherence gives a powerful answer to why superpositions are not observable at large scales. It does not force every philosopher or physicist to accept one interpretation. This is why Schrödinger's cat remains alive as a conceptual problem, though perhaps not in the way popular culture imagines. The cat is not waiting for a human mind to create reality. The cat is showing us that quantum mechanics needs an account of outcomes. Decoherence explains the loss of interference. Interpretations explain what to say about the remaining branches or a collapsed result. Now, let us make the physical picture more concrete. Imagine a small quantum system in a superposition of two positions, left and right. If isolated, those alternatives can interfere. Now let one photon scatter from the particle. If the photon scatters differently, depending on whether the particle was left or right, the photon carries which position information. The particle and photon become entangled. If we ignore the photon, the particle alone no longer behaves like a clean, coherent superposition. Its interference is reduced. Now, imagine many photons scattering, many air molecules colliding, many vibrations coupling. Information about left and right spreads into the environment. To restore the interference, we would need to collect every environmental particle and reverse the entanglement perfectly. Every photon, every molecule, every vibration, every tiny trace. For a small laboratory system, this is already hard. For a macroscopic system, it is effectively impossible. This is why decoherence is so powerful. It turns a delicate quantum relation into a practical irreversibility. It is closely connected to entropy and information spreading. The phase information is not simply erased, it is exported into the environment. Like ink dissolving into water, like a whisper lost in a stadium, like a pattern written into too many scattered pages. The information may exist in the full state, but no local observer can use it to produce interference again. This is why the classical world feels definite. Because the alternatives that would reveal quantum strangeness are no longer available to us. They have become woven into the environment. A coherent superposition is like a carefully tuned chord. Decoherence is what happens when each note is copied into 1,000 echoing rooms, each slightly different, until the original chord can no longer be heard as one sound. The music is not gone. It is everywhere. And because it is everywhere, it is no longer recoverable as a clean pattern. This is a metaphor, but the physics is precise. Entanglement with the environment suppresses interference between components of a superposition. The larger the system, the faster this usually happens. The stronger the environmental coupling, the faster it happens. The more distinguishable the alternatives, the faster it happens. A cat alive and a cat dead are extremely distinguishable, macroscopic alternatives. So decoherence would be unimaginably fast. This does not mean quantum effects are absent from biology altogether. Quantum mechanics is essential for chemistry. Chemical bonds, electron orbitals, molecular structure, photosynthesis, enzyme behavior, vision, all depend on quantum physics at some level. But that is different from saying a whole organism remains in a coherent superposition of macroscopically distinct life states. Quantum mechanics underlies the cat. But the cat does not behave like a clean qubot. A qubot is carefully engineered and protected. A cat is a living macroscopic system. Again, the distinction is not quantum versus non-quantum matter, it is coherent versus Descartes behavior. This is a better way to think. Not small things are quantum, and big things are classical, as a hard law. Instead, systems can display quantum coherence when they are sufficiently isolated and controlled. Systems appear classical when interactions with the environment rapidly decohere. The relevant superpositions. Size matters because larger systems tend to have more interactions. Temperature matters because warmer systems have more thermal motion and radiation. Complexity matters because there are more channels for information to leak. Environment matters because entanglement spreads. This gives us a smoother picture of the quantum classical boundary. A boundary not drawn with a ruler, but with interaction. The more isolated the system, the more quantum interference can remain. The more entangled with the environment, the more classical it appears. This is why modern experiments are so interesting. Physicists try to push quantum behavior into larger systems. Molecules, superconducting circuits, tiny mechanical resonators, cold atomic clouds, engineered quantum devices. They create environments quiet enough for coherence to survive. They are not proving that quantum mechanics is mystical. They are showing how delicate coherence can be and how far it can be extended. Every successful experiment sharpens the question: how large can a quantum superposition be? How long can coherence survive? What destroys it? Can we control decoherence? Can we use it? Can we build quantum computers despite it? In this way, Schrödinger's cat is no longer only a philosophical image. It is connected to real experimental physics. Quantum information, quantum computation, macroscopic quantum states, decoherence control, measurement theory. The cat's box has become a laboratory theme, not with actual cats, but with systems where the same foundational questions can be tested more safely and precisely. A superconducting qubot, for example, can be in a superposition of two electrical states. These states may involve many electrons behaving collectively. The system is cooled to extremely low temperatures, shielded, controlled, measured. Physicists fight decoherence to preserve the quantum state. The qubot is not a cat, but it is a step toward understanding how quantum behavior scales. There are also experiments with molecules showing interference. Larger and larger molecules have been sent through interferometers. Their interference patterns show that quantum superposition can apply to systems larger than single atoms, but again, only when conditions are carefully controlled. The larger the object, the more the environment must be silenced. This is one of the most practical lessons of decoherence. Quantum behavior is not rare because the universe dislikes it. Quantum behavior is everywhere underneath, but visible quantum interference is rare because the environment is loud. The world is full of uninvited witnesses: photons, air molecules, thermal vibrations, surfaces, fields. Each one can carry away a trace. Each one can help classical reality appear. So, when someone says the cat is both alive and dead, until we look, the careful response is softer and sharper. The formal quantum description of the isolated system may contain correlated alternatives, but a real macroscopic cat would decohere almost instantly due to interaction with its environment. Human observation is not the magic trigger. The physical environment is already involved. The remaining question is interpretive. What do we say about the Dacre branches? Are they all real? Did one collapse? Was the wave function only a predictive tool? That is where interpretations enter. Decoherence gives us the bridge. It explains how quantum superpositions become classical appearances. But once we cross the bridge, we still need to decide what kind of landscape we believe we are standing in. That will be the next part of the journey. The interpretations of quantum mechanics. Copenhagen. Many worlds. Objective collapse. Pilot wave. And other attempts to say what the mathematics is really telling us. Not as competing bedtime myths, but as serious efforts to answer the question Schrödinger placed inside the box. Quantum mechanics works. That is the first thing to say before discussing interpretations. Its predictions have been tested again and again. Atoms, photons, electrons, lasers, semiconductors, magnetic resonance imaging, quantum tunneling, superconductors, modern electronics. Much of the technological world quietly depends on the accuracy of quantum theory. The disagreement is not usually about whether the equations work. They do. The disagreement is about what the equations mean. What is the wave function? What is a measurement? What happens when we observe one outcome? Does the wave function collapse? Do all outcomes continue in separate branches? Are there hidden variables guiding the results? Is the wave function a real physical object or a tool for assigning probabilities? These are interpretation questions, and Schrödinger S-cat is one of the simplest ways to force them into view. Place an atom, detector, mechanism, and cat inside the box. Let the atom be linked to two possible outcomes. Then ask what the quantum state of the whole box means before it is opened. Different interpretations answer differently. They often make the same predictions for ordinary experiments, but they tell different stories about reality. This is why interpretations are both fascinating and dangerous. Fascinating because they ask deep questions. Dangerous because they are easy to turn into slogans. So tonight, we will move carefully. Not choosing a favorite too quickly. Not pretending that one paragraph can settle a century of debate. Just looking at the main ideas calmly. The first interpretation family to discuss is Copenhagen. The Copenhagen interpretation is associated with Niels Bohr, Werner Heisenberg, and the early development of quantum mechanics. It is not one perfectly fixed statement. Different physicists have used the phrase in slightly different ways. But broadly, Copenhagen emphasizes the role of measurement and the limits of describing quantum systems as if they had definite classical properties before measurement. In this view, the wave function is used to calculate probabilities for measurement outcomes. Before measurement, it may not be meaningful to say that the system already had one definite value for the measured property. The act of measurement produces a definite outcome. After measurement, the wave function is updated to reflect that outcome. In practical quantum mechanics, this works extremely well. Prepare a system. Calculate probabilities, measure, get an outcome. Update the state. Repeat. Copenhagen is often described as pragmatic. It tells scientists how to use the theory. It warns us not to demand classical pictures where quantum theory does not provide them. But it can feel incomplete if we ask, what exactly counts as a measurement? Where is the boundary between quantum system and classical apparatus? Is collapse physical, or just a change in knowledge? Does the wave function represent reality, or our information about possible outcomes? Different Copenhagen-like views answer these questions differently. For Schrödinger's cat, a Copenhagen-style response might say that the sealed system cannot be assigned a classical outcome until measurement is made in the experimental context. The wave function gives probabilities. Opening the box yields one result, alive or dead. But Schrödinger's challenge remains. If the cat, detector, and apparatus are all made of quantum matter, why should the line be drawn at the observer or apparatus? What makes measurement special? That is the pressure point. Copenhagen gives a useful working framework, but for many people, it leaves the deeper physical story partly unfinished. Now consider the many worlds interpretation. Many worlds was proposed by Hugh Everett in 1957. Its central idea is bold. There is no collapse of the wave function. The wave function always evolves smoothly according to quantum mechanics. When a measurement-like interaction occurs, the system, apparatus, observer, and environment become entangled. Different outcomes become different branches of the universal wave function. In one branch, the detector clicks. In another, it does not. In one branch, the cat is alive. In another, the cat is dead. The observer in each branch sees a definite outcome. The branches do not interfere because decoherence separates them effectively. This interpretation takes the mathematics very seriously. It says, do not add collapse, let the wave function evolve. The cost is that all outcomes occur in branching worlds, or branches of the universal state. That idea can sound extravagant, many worlds, many copies, many branches. But supporters argue that it is mathematically clean. It does not require a special measurement postulate. It does not require a fuzzy boundary between quantum and classical. Measurement is just entanglement and branching. Decoherence explains why branches do not interfere. For Schrödinger's cat, many worlds gives a direct answer. There is a branch with a live cat and a branch with a dead cat. Opening the box entangles the observer with one branch. Each observer sees one outcome. There is no single collapse. The full wave function contains both. This is elegant in one way and unsettling in another. It removes the collapse problem, but accepts a vast branching reality. The challenge becomes explaining probability. If all outcomes occur, what does it mean to say one outcome is more probable than another? Many worlds has developed sophisticated answers involving branch weights and the Born rule, but debates remain. Still, it is a serious interpretation, not science fiction decoration. Not a portal fantasy, a rigorous attempt to keep the quantum equations universal and unbroken. Now consider objective collapse theories. These interpretations say that wave function collapse is real. Not just an update in knowledge, not just an observer's experience, a physical process. In standard quantum mechanics, collapse is not described by the Schrödinger equation, it is added as a measurement rule. Objective collapse models try to modify quantum mechanics so that collapse happens spontaneously under certain conditions. Often, the probability or rate of collapse increases with the size or complexity of the system. Small systems can remain in superposition. Large systems collapse quickly into definite states. This would explain why electrons can show quantum interference, while cats do not. The collapse is built into the physics. Examples include GRW theory, named after Garrotti, Rimini, and Weber, and related models. These theories make slightly different predictions from standard quantum mechanics in some regimes. That is important. Unlike interpretations that are empirically equivalent in ordinary cases, objective collapse models may be testable. Experiments can look for tiny deviations from standard quantum behavior. For Schrödinger's cat, an objective collapse view might say that the cat does not remain in a superposition because the large system undergoes physical collapse extremely quickly. One outcome becomes real, the other does not. This feels closer to ordinary experience, but it requires changing the dynamics of quantum theory. Adding collapse as a real physical process, that raises questions. What exactly triggers collapse? What parameters control it? Can experiments detect it? Does it fit with relativity? Objective collapse theories are serious because they try to turn the measurement problem into new physics. They do not simply reinterpret the mathematics, they modify it. Now consider pilot wave theory, also known as de Broglie-Bohm theory or Bohmian mechanics. This interpretation keeps particles with definite positions. Particles follow trajectories, but they are guided by a wave function. The wave function evolves according to Schrödinger's equation and directs the motion of particles through a guiding equation. In this view, the randomness of measurement outcomes arises from uncertainty about the initial positions of particles, not from the absence of definite reality. The theory is deterministic at the underlying level, but it is also non-local means that distant parts of the system can be connected in ways that do not fit classical local intuition. This non-locality is not optional. Bell's theorem and experiments have shown that any hidden variable theory reproducing quantum predictions must have strange non-classical features. For Schrödinger's cat, pilot wave theory would say the particles in the box always have definite positions. The cat is either alive or dead in the actual configuration. The wave function may contain branches, but only one branch contains the actual particle configuration. The other branch is sometimes called an empty wave. This avoids the idea of a cat literally lacking a definite outcome. But the cost is a non-local guiding structure and a wave function with a real role in configuration space. Pilot wave theory is clear and realist. It gives a definite ontology. Particles have positions, but it is not a return to simple classical physics. It is deeply quantum and non-local. Now consider relational interpretations in relational quantum mechanics, associated with Carlo Rovelli and others. The state of a system is not absolute in the same way classical properties are imagined to be. Properties are defined relative to other systems through interactions. A measurement is an interaction that establishes facts relative to the systems involved. This view tries to remove the need for a single universal observer-independent state that assigns definite properties everywhere at once. For Schrödinger's cat, the state of the cat may be definite relative to the cat or internal apparatus, while still described differently relative to an outside observer. This sounds strange, but it reflects the idea that quantum states are relational, not necessarily a view from nowhere. The challenge is to make clear how different relational facts fit together consistently. Another family of views treats the wave function as information or belief. Quantum Bayesianism, often called cubism, is one example. In cubism, the wave function represents an agent's personal degrees of belief about future experiences or measurement outcomes. It is not a physical wave out in the world. Measurement is an action by an agent, and the outcome is an experience for that agent. The wave function updates when the agent receives new information. This approach avoids some puzzles by changing what the wave function is supposed to represent. It is not a literal physical object that collapses. It is a tool for assigning probabilities. For Schrödinger's cat, the quantum state assigned to the box reflects the observer's expectations about possible experiences when opening it. The cat paradox becomes less about a physical live-dead wave and more about how agents use quantum theory to organize expectations. This is philosophically radical in a different direction. It moves the mystery from physical collapse to the meaning of probability, experience, and agency. Some physicists find it clarifying. Others find it too subjective. Again, the cat asks each interpretation to show its price. Every interpretation has a cost. Copenhagen is practical, but can leave measurement conceptually vague. Many worlds keep smooth evolution, but accepts branching reality. Objective collapse gives real outcomes, but modifies quantum dynamics. Pilot wave theory restores definite particle positions, but requires non-local guiding behavior. Relational approaches change the status of properties. Cubism changes the status of the wave function into an agent-centered probability tool. There is no free interpretation. Each one pays somewhere. This is why the measurement problem has lasted so long. It is not that physicists are confused about how to calculate. The calculations are clear. The issue is what kind of reality we think the calculations describe. Schrödinger's cat is a test of that reality picture, not an experiment about animal biology, not proof of consciousness magic, not a license to say anything, a conceptual stress test. A way of taking a small quantum superposition and connecting it to a large ordinary outcome, then asking, what do you believe happened? This is also why we should be careful when saying the cat is both alive and dead. In Copenhagen language, one may say the state before measurement is a superposition relative to the experimental description. In many worlds, both outcomes exist in different decoherent branches. In collapse theories, one outcome becomes real through physical collapse. In pilot wave theory, the actual configuration corresponds to one outcome, while the wave function may contain other components. In information-based views, the statement may describe expectations rather than direct reality. The phrase means different things in different interpretations. So the simple, popular sentence hides an entire philosophical map. Alive and dead is not a final answer. It is the beginning of the question. Now, which interpretation is correct? At present, there is no universal agreement. Some interpretations are empirically equivalent in most known experiments, meaning they give the same predictions. Others, like objective collapse models, may lead to testable deviations. Physicists choose interpretations for many reasons: mathematical elegance, ontological clarity, compatibility with relativity, treatment of probability, attitude toward observers, willingness to accept branching worlds, willingness to modify the theory, willingness to treat the wave function as real or informational. There is no simple pole that settles reality. Science settles questions through evidence, consistency, explanatory power, and sometimes new experiments. The foundations of quantum mechanics remain active because the evidence constrains the theory strongly, but does not force one single interpretation in every respect. That uncertainty should not be embarrassing. It is honest. Quantum mechanics is one of the most successful theories ever created, and still its meaning remains deep. That is not a failure. It is a sign that the theory reached a level where our old categories were not enough. Particle, wave, measurement, outcome, reality, knowledge, observer, system, environment. Each word had to be sharpened. Schrödinger's cat is famous because it cuts all those words at once. Now, for our purposes, the most important scientific message is this. The cat does not show that consciousness creates reality. The cat does not show that everything exists in all states until a person looks. The cat does not show that human thoughts control quantum outcomes. The cat shows that quantum theory must explain the transition from superposition to definite observed outcomes, and modern physics brings decoherence into that explanation. The environment spreads phase information. Macroscopic alternatives stop interfering. Classical reality appears. Interpretations then tell different stories about what that appearance means at the deepest level. This is the clean way to hold the paradox. Superposition is real in the quantum formalism. Interference shows that it is not ordinary ignorance. Measurement produces definite records. Decoherence explains why large systems look classical. Interpretations debate what is ultimately happening. No glitter, no fog machine, no cosmic wish engine, just physics. And physics is already strange enough. A photon can build an interference pattern one dot at a time. Entangled particles can violate Bell inequalities. A wave function can describe alternatives with complex amplitudes. A detector can become correlated with a quantum system. The environment can hide interference by spreading information everywhere. A sealed box can force us to ask what reality means. We do not need to add magic to make this astonishing. The real quantum world is quieter, sharper, and more demanding. As we move toward the final part of the video, we can now ask what Schrödinger's cat actually teaches us. Not the slogan, not the meme, not the mystical version, the real lesson. It teaches us about superposition, measurement, decoherence, the quantum classical boundary, and the humility required when a theory works perfectly in the lab while still asking us what we mean by reality. So what does Schrödinger's cat actually teach us? Not the slogan, not the joke, not the mystical version, the real lesson. The first lesson is that quantum superposition is not ordinary ignorance. If a coin is hidden under a cup, it is either heads or tails. We may not know which, but the coin is not in a quantum superposition just because we have not looked. Quantum superposition is different because the alternatives can interfere. A photon in a double-slit experiment can behave as though different path alternatives are combined. Those alternatives can reinforce or cancel to produce an interference pattern. That is not classical uncertainty. So when we talk about the radioactive atom, we are not simply saying we do not know if it decayed. In the quantum description, before measurement, the atom may be represented as a superposition of decayed and not decayed. That superposition is a physical part of the formalism. It is what allows quantum mechanics to predict interference, probabilities, and experimental results. But the second lesson is just as important. A cat is not a clean microscopic quantum system. A cat is not a photon, not an electron, not a carefully isolated atom in a trap. A cat is a warm, complex, macroscopic living system. It is made of an enormous number of particles. It interacts constantly with its environment. It emits heat. It scatters photons. It exchanges air molecules. It undergoes chemical reactions. Its internal state is not quiet. It is a storm of physical activity. So when the cat becomes linked to the detector, the system does not remain a neat, observable, coherent superposition in any practical sense. The alternatives become entangled with the environment. Information leaks outward. Phase relationships become inaccessible. Interference between the alternatives becomes effectively impossible to observe. This is decoherence. Decoherence is not magic. It is not consciousness. It is not a mysterious force choosing reality. It is ordinary quantum interaction with many environmental degrees of freedom. The environment becomes correlated with the system. The alternatives stop interfering. The classical world appears. This is one of the most important modern lessons from the cat. The reason we do not see cats in visible superpositions is not that human minds are constantly rescuing reality. It is that macroscopic systems interact with their environments too strongly and too quickly. The world is always making records. Photons, air molecules, thermal radiation, surfaces, detectors. Everything touches everything else. And those interactions make coherent macroscopic superpositions extraordinarily fragile. The third lesson is that measurement is physical. A measurement is not simply a person looking. It is not mystical attention. It is not the universe waiting for consciousness. In real experiments, measurement involves interaction, correlation, amplification, and record formation. A detector absorbs radiation. A screen records a spot. A circuit changes state. A signal is amplified. A memory device stores a bit. A mark is left. Measurement creates a physical record, and that record can exist whether or not a human watched the event happen in real time. A detector can click in an empty laboratory. A camera can record light before anyone sees the image. A computer can store data before anyone opens the file. The physical process does not pause for human awareness. This does not mean observation is irrelevant in the practical sense. Scientists still need to read instruments and compare results. But in quantum mechanics, the physical measurement process is not the same as conscious attention. That distinction keeps the science clean. The fourth lesson is that the wave function is powerful, but its meaning is debated. Quantum mechanics tells us how to use the wave function. It tells us how to calculate probabilities. It tells us how systems evolve when isolated. It tells us how to predict experimental outcomes. But what the wave function is remains an interpretation question. Is it a real physical object? Is it a complete description of reality? Is it a tool for assigning probabilities? Is it information? Is collapse real? Or does the wave function never collapse? Different interpretations answer differently. This is why Schrödinger's cat remains useful. It forces each interpretation to explain what is happening in the box. Copenhagen must explain the role of measurement and classical outcomes. Many worlds must explain branching and probability. Objective collapse theories must explain when and how collapse occurs. Pilot wave theory must explain the role of definite configurations and the guiding wave. Information-based interpretations must explain what the quantum state represents for an observer or agent. Every interpretation must pay its bill. There is no free interpretation. The cat asks each one to show its receipt. The fifth lesson is that the quantum classical boundary is not a simple wall. There is no obvious line in nature where quantum mechanics suddenly stops. Small systems are quantum. Large systems are made of quantum parts. Detectors are made of atoms. Cats are made of atoms. Observers are made of atoms. So the question is not whether the large world is secretly non-quantum. The question is how quantum behavior becomes classical appearance. Decoherence gives much of the answer. As systems grow larger, warmer, more complex, and more entangled with the environment, coherent superpositions between macroscopically different alternatives become effectively unobservable. The classical world is not separate from the quantum world. It is the quantum world after its delicate phase. Relationships have been dispersed into the environment. That idea is subtle and beautiful. The classical world is what quantum mechanics looks like when the environment has taken too many notes. The sixth lesson is that Schrödinger was not trying to make quantum mechanics sound mysterious for fun. He was showing a problem. He wanted us to notice the strange consequence of applying quantum superposition directly to a macroscopic system. The cat was not an explanation. It was a challenge, a warning, a magnifying glass placed over the measurement problem. Schrödinger was asking, if this is what the theory implies, have we really understood the theory? That question still matters. Not because quantum mechanics is weak, but because it is strong enough to force us to be honest. Its predictions work. Its mathematics works. Its technology works. But its meaning still asks for care. The seventh lesson is that the popular phrase, alive and dead, should be handled gently. It is useful as a shorthand, but it is dangerous as a final statement. In the full story, the cat is not simply a magical object occupying two ordinary states in a cartoonish way. The cat is part of a large entangled system. Atom, detector mechanism, cat, environment, observer. The phrase alive and dead compresses all of that into 4 words. Sometimes compression helps. Sometimes it distorts. In this case, it often a better sentence might be this. The quantum formalism can describe the sealed box as a superposition of correlated alternatives, and the paradox asks how such a description relates to the definite outcome we observe. That sentence is less catchy. It would not fit well on a mug, but it is closer to the physics. The eighth lesson is that quantum mechanics is strange enough without exaggeration. We do not need to say, consciousness creates the universe. We do not need to say, every wish exists in another quantum state. We do not need to turn uncertainty into spirituality. The real experiments are already astonishing. Single particles build interference patterns. Entangled systems violate classical expectations. Detectors turn microscopic events into macroscopic records. Quantum states evolve with amplitudes and phases. Decoherence hides interference in the environment. The real theory does not need theatrical fog. It has its own night sky. Deep, quiet, precise, and difficult. The ninth lesson is humility. Quantum mechanics teaches humility because it works better than our intuition. Our intuition evolved for stones, animals, tools, light, sound, motion, and everyday objects. It did not evolve for wave functions in Hilbert space. It did not evolve for entangled particles. It did not evolve for non-commuting It did not evolve for quantum measurement. So when quantum mechanics feels strange, that does not mean it is vague. It means our everyday categories are being asked to do work they were not built for. Words like particle and wave are approximations. Words like observe and measure need sharpening. Words like real and possible become harder. This is why good quantum explanations should not flatten the strangeness too much, but they should not inflate it into fantasy either. The correct path is narrow. Keep the mathematics respected. Keep the experiments central. Keep the mystery honest. That is where the cat belongs. Not in a mystical self-help lecture. Not in a cartoon universe where anything means anything. But in the serious foundations of quantum mechanics. A sealed box. A probabilistic atom. A detector. A macroscopic record. A question about what measurement means. And a reminder that reality may not fit comfortably inside the classical pictures we prefer. So what should we say, finally, about the cat? Was it really both alive and dead? The careful answer is this. In the thought experiment, if we apply the quantum formalism to the entire sealed system, the wave function can contain a superposition of correlated alternatives, one corresponding to the cat alive and one corresponding to the cat dead. But in any realistic macroscopic situation, decoherence would make interference between those alternatives effectively impossible. What this means ontologically depends on interpretation. Copenhagen, many worlds collapse theories, pilot wave theory, and information-based views do not say exactly the same thing. So the cat is not a settled slogan. It is a doorway into the measurement problem, a doorway into decoherence, a doorway into the quantum classical transition, a doorway into the meaning of the wave function. And perhaps that is why the image survived. Because it is simple enough to remember, but deep enough to remain unresolved. A cat in a box, a tiny atom, a detector waiting, a universe of questions folded into a sealed system. The true lesson is not that reality is controlled by looking. The true lesson is that measurement is one of the deepest physical ideas we have. It is where possibility meets record, where amplitude meets outcome, where the quantum world becomes the classical world we can write down, photograph, share, and remember. And now, as we approach the end of this journey, we can let the box close again. Not because the question is finished, but because we can now see what was really inside. Not just a cat, a paradox, a boundary, a theory that works beautifully, and a mystery that refuses to become cheap. And now, we can leave the box where Schrödinger placed it, closed, quiet, and still asking its question. We began tonight with one of the most famous images in all of physics, a cat in a sealed box, a radioactive atom, a detector, a mechanism, an observer outside, waiting. It is an image that has traveled far beyond the laboratory, into books, classrooms, jokes, posters, internet arguments, and too often, into explanations that make quantum mechanics sound softer, easier, or more magical than it really is. But tonight, we tried to keep the cat inside physics, not inside mysticism, not inside wishful thinking, not inside the idea that consciousness casually creates the world, inside physics, where the real mystery is already deep enough. We saw that Schrödinger's cat was not invented as a cute example. It was invented as a warning, a challenge to the way quantum theory was being interpreted. Schrödinger wanted to show what happens when a microscopic quantum superposition becomes linked to a macroscopic outcome. An atom decays, or it does not. A detector triggers, or it does not. A mechanism activates, or it does not. The cat lives, or it dies. If the entire sealed box is described by a wave function, the formalism seems to contain correlated alternatives. And that is where the discomfort begins. Not because cats are magical, not because observers have supernatural power, but because quantum measurement is difficult. We saw that superposition is not ordinary ignorance. A coin hidden under a cup is not in a quantum superposition just because we have not looked. It is either heads or tails. We simply do not know. Quantum superposition is different. It involves amplitudes, phase, interference. A quantum system can behave as a combination of alternatives in a way that ordinary classical uncertainty cannot. That is why the double-slit experiment matters. That is why interference matters. That is why the word superposition must be handled carefully. It is not a poetic maybe. It is a mathematical and experimental feature of quantum theory. We looked at the wave function, that strange and powerful object at the center of quantum mechanics, a tool that lets physicists calculate probabilities with astonishing precision, a structure that evolves smoothly when systems are isolated, a structure whose meaning remains debated. Is it real? Is it information? Is it complete? Does it collapse? Does it branch? Does it guide particles? Does it describe knowledge, reality, or something harder to name? Quantum mechanics gives correct predictions, but the interpretation of those predictions remains a careful, open conversation. We saw that measurement is not simply a person looking. Observation is not magical attention. Measurement is physical. A detector changes. A screen records a mark. A circuit stores a signal. A device becomes correlated with a system. A record forms. The world does not wait for a human mind before it begins interacting. Photons scatter, air molecules collide. Heat radiates. Surfaces vibrate. Information leaks outward. The environment is always involved. And this led us to decoherence, one of the most important bridges between the quantum and classical worlds. Decoherence explains how delicate phase relationships in a superposition become dispersed into the environment. It explains why interference between macroscopic alternatives becomes effectively impossible to observe. It explains why large warm objects look definite, why detectors have stable readings, why chairs do not appear in two places at once, why cats do not appear as visible, alive, Van dead interference patterns. The classical world is not separate from the quantum world. It is the quantum world after its delicate coherences have been spread too widely to recover. A quiet but powerful idea, the quantum does not vanish. It becomes hidden in the environment. We also looked at interpretations. Copenhagen, many worlds, objective collapse, pilot wave theory, relational views, information-based approaches. Each tries to answer the same question from a different angle. What does the wave function mean? What happens during measurement? Why do we observe one outcome? Does collapse occur? The branches continually are particles guided by hidden variables? Is the quantum state information rather than physical substance? No interpretation is free. Each pays a price. Some pay with a measurement cut, some with branching worlds, some with new collapse physics, some with non-local hidden variables, some with a changed meaning of physical state. And the cat asks all of them to be clear. That is why the paradox survives. Not because the slogan is simple, but because the question is hard. So now, when we hear the phrase Schrödinger's cat is both alive and dead, we can hear it more carefully. It is not a final answer. It is a compressed doorway, a shorthand for a much deeper issue. The quantum formalism can describe the sealed box as a superposition of correlated alternatives between the wave function and the world of definite experience, between microscopic coherence and macroscopic stability, between the mathematics that works and the meaning we are still trying to understand. That boundary is not a simple wall. There is no sign in nature that says, quantum ends here, classical begins here. There are systems, interactions, environments, records, degrees of freedom, coherence preserved, coherence lost, information hidden, information amplified. Small quantum events becoming large classical facts. The boundary is not painted onto reality, it emerges. And perhaps that is why the cat remains so powerful, because it waits exactly where our language becomes strained. We want to say, the atom decayed or did not decay. The detector triggered or did not trigger. The cat lived or died. The outcome happened or did not happen. But the quantum formalism asks us to slow down, to ask what we mean by happened, to ask what we mean by state, to ask what we mean by measurement, to ask what we mean by reality before a record is made. These are not easy questions, but they are good questions. And good science does not always remove mystery. Sometimes it refines it. It takes a vague mystery and makes it sharper. It removes the fog, it keeps the difficulty. That is what we tried to do tonight. To remove the fog from Schrödinger's cat. No quantum manifestation, no magical observer, no cheap uncertainty, just the real difficulty. A difficulty precise enough to be scientific. A difficulty that has shaped experiments, theories, technologies, and debates for nearly a century. This is the beauty of the paradox. It does not tell us to believe anything we like. It tells us to be careful. Careful with words, careful with images. Careful with the difference between not knowing and superposition. Careful with the difference between consciousness and measurement. Careful with the difference between decoherence and collapse. Careful with the difference between calculation and interpretation. The cat is famous because it is vivid, but it is valuable because it is demanding. It asks for discipline. It asks for clarity. It asks us not to confuse wonder with looseness. The real quantum world is strange, but it is not vague. It is probabilistic, but not careless. It is difficult, but not decorative. It is mysterious, but not a blank check for fantasy. That may be the final lesson tonight. Science does not make the universe less beautiful by refusing easy magic. It makes the beauty harder, cleaner, and more durable. A photon crossing an experiment, an atom waiting to decay, a detector ready to click, a wave function evolving, a record forming, an environment taking notes, a classical world appearing from quantum rules. This is already enough, more than enough, so we can let the box close gently. Not as an ending to the question, but as a place where the question can rest. Inside it, not a simple answer, not a slogan, not a trick, but a boundary. The quiet boundary between quantum and classical, between what can interfere and what has become recorded, between the hidden mathematics of possibility and the world where one result is written down. Thank you for spending this calm journey with Midnight Science. If you are still awake, you can let the final image stay for a little while. A dark desk, a sealed box, a faint blue wave fading into the room, a detector silent in the corner, a notebook open to an unfinished question. No magic, no noise, just physics. Still thinking? Sleep well, and good night.